Hey everybody, thanks for showing up. All right, first thing I'd like to do real quick, I think I told you in class I wouldn't make you do anything too crazy with these numbers, but that being said, if so that's why I wrapped this thing through my shirt up here. All right. Okay, so for the compliance equation, we had it worked out like this, where we had the compliance of the total system, the chest wall, and then the individual compliance of the lung. And if we had some numbers that were real easy to deal with, we could probably do this in our head if we had to solve for total compliance. We're given each of the individual chest wall and lung compliances. If we were to, let's say, manipulate just one of these. Let's say that we are trying to figure out what the total compliance is after we've changed one of these individual compliances. So we'll say that we go ahead and change the individual compliance of the chest wall to 0.5 from a normal 0.2. Leave the lung compliance alone, and then we'll try to figure out what's happening to the total system compliance as a result of that change in the chest wall compliance. So what we could do here is divide 1 by 0.5, and 0.5 goes into 1 2 times. And then we would have our regular number there, and we're left with 1 over x. Now let's say we get to this point and we can't really figure out what to do with this fraction or how to solve it. Our calculator has a nifty number to help us out there, and it's like you have one of these buttons on the Respondus Lockdown browser calculator. I double checked before I came in here today, and let's say that we've worked our math down to the point where we're at this step here where we had 7. If we want to figure out what this variable x would be, we just put in our 7 and then click the 1 over x button. And that'll tell us what the unknown is. So the unknown would be 0.143. So that would be the new total compliance. So to solve for 1 over an unknown, we could just whittle the equation down on one side to deal with a number, and then just hit the 1 over x button. Okay, so not too bad. If you need to double check what you're doing or make sure that your answer makes sense, this would be a good way to go about doing that. You know, we didn't really have too many sample questions to work on that would tell us, you know, how to do this for Friday. If you do need to deal with some numbers and are backed into a corner solving or trying to double check for 1 over x, this would be how to do it. So not too bad. Okay, and then it would kind of make sense here. If we go ahead and increase the compliance of the chest wall, it's going to increase the compliance of the system, but not by as great of a degree as just the individual increase in the chest wall compliances, because we're still dealing with the normal lung compliance, so it'll affect the overall system compliance, but not as much as the degree by which it's just changing the chest wall compliance. Okay, so I wanted to just run through that with you. Hopefully that'll be useful. Any questions on that? Can I erase this? Okay. All right. So on test day, your lockdown browser, it's got one of those 1 over x buttons, and it's one of those buttons that no one ever uses ever. this is the one place where we can go ahead and use that. All right, another thing, just wanted to make sure that we're all clear on. If we're trying to find hemoglobin saturation, it's usually expressed in percentage. And that would be quantity of oxygen that we have bound to hemoglobin over the carrying capacity of hemoglobin. So if we have a quantity of hemoglobin, we can figure out how much oxygen that hemoglobin can carry. And then if we know the total amount of oxygen hanging around in the system, or quantity, more specifically, the quantity that's actually bound to hemoglobin, it would just be that ratio there. So that's how it sets us up for a percentage. So it's a ratio. So that's how we end up getting a percentage all the time. All right. So that's what we had up here at the beginning of the last test. I put that up here real quick in the on the board to hopefully just remind everybody of that. And so we'll do that again here. I won't put it up on Friday again. So this will be. Yeah, Jameson.
Unless you differentiate, do you want us to use the 97.5 for the total carrying capacity, or assume just 100% and go with the 20.1?
I think for almost everything on the last test, we were okay with doing 100%. If I ask you, I'll put it in the question to ask you to be real specific if we have to do that, definitely. It's a good question. All right. And
I had a question about that equation.
Okay.
I think I got tripped up on the exam. Can you hear me okay?
Yeah, yep.
Okay. I think I just got tripped up because I thought that the amount of hemoglobin that we had, regardless of if, we were anemic or it was normal, we could still have 100% saturation of that hemoglobin. So I think that's just kind of what confused me.
Yeah. I think that's totally understandable, and that kind of takes us into the next thing that I wanted to just chat about real quick. So if so maybe hopefully this will help us out. Okay, so we know what a normal amount of hemoglobin is. If we have an abnormal amount of hemoglobin, I think we've seen a situation before where we may have a hemoglobin of 10, so it's considerably less than normal. Then what we would have for our carrying capacity would be 1.34 times 10, so 13.4 mLs of oxygen would be the carrying capacity of that quantity of hemoglobin. And if we were to think about what the blood gases would be in somebody with anemia, in terms of their ABGs, those should look pretty normal as long as they're not too crazy anemic or really deathly ill or anything. So their ABGs should look fairly normal. I think there were a couple items in the Levitsky book that said that there would be a few things that would be normal. And the normal parts of their blood gases should probably consist of the PaO2 being around 100 millimeters of mercury. And then if we have a PaO2 of 100 millimeters of mercury, that would give us, this would probably be enough pressure to saturate our hemoglobin with oxygen or get us awfully close to that, so 97.4 or 100. So we can probably go with 100 there. So if we have a PaO2 of 100, we'd probably assume that our SAT is pretty high, so 98 to 100 or thereabouts. And their PaO2 is going to be normal. So as long as this is somebody who isn't, again, crazy sick, if this is describing somebody at rest who has anemia, they probably wouldn't be hyperventilating or anything because their arterial blood gases are normal. So our chemoreceptors are usually looking at the PaO2 and PaCO2, so that those are normal. There's not going to be, shouldn't be any abnormal breathing or anything at rest. But what the one thing is that would be normal would be the oxygen content. So if we only have 13.4 mLs of oxygen as our carrying capacity, if we're breathing room air, then our PaO2 is going to be about 100. So there we've really limited the quantity of oxygen that's being delivered to the peripheral tissues. So our CaO2 would be somewhere in the ballpark of 13.4. And again, we could probably be a little bit more accurate for this number if we wanted to push it, but for most of the stuff that we ran into on the last test, it would work if we do just use the simple method here. So it's about what the carrying capacity is, so the content equals close to the carrying capacity. And if this is what's being delivered to the peripheral tissues, the peripheral tissues are pretty much just going to take what they need and take what they're used to taking. So our kidneys don't really run well on an oxygen deficit whatsoever. So if we have less oxygen being delivered to the kidneys are just going to keep grabbing the normal amount of oxygen that they grab, which would be about 5 mLs of oxygen being extracted from each deciliter of blood that's passing through the periphery. So normally our arterial content is about 20 and our venous content is 15. The difference between that is 5 mLs of oxygen per deciliter of blood. And again, generally speaking, the peripheral tissues are just going to take what they need. So if we end up delivering less to those tissues, so if we deliver 13.4 and they're still grabbing 5, then what we're going to be left over with is probably 8.4 mLs of oxygen. So if we were to look at SVO2 or try to figure out SVO2, what we would do is we'd look at, well, what's the carrying capacity? That's that number. And what is the amount of oxygen that we have hanging around? So it's 8.4. So if we divide 8.4 by 13.4, we get somewhere in the mid-60s for a SVO2. So that would be our venous hemoglobin oxygen saturation. So in somebody who's anemic, they're probably going to have lower quantities of oxygen everywhere compared to normal. Really doesn't show up in the pressures in an arterial sample. But what it does show up in big time is SVO2. And parallel with that, we'd probably also expect to see a lower than normal PVO2. Normally it's 40. Here, if we have less oxygen than we normally do, that number is going to be lower than normal. So the fact that the tissues pretty much just take what they need, that's the basis of you using SVO2 monitoring in someone who has heart failure. So if you look at SVO2, you're trying to figure out, is the heart failure getting worse? Is it getting better? Most of the time it's getting worse. The lower the SVO2 is, the crappier the heart is pumping oxygen to the tissues. So the worse the heart is, usually the lower our SVO2 is. And we can correlate that with pumping efficiency or oxygen delivery from the lungs via the left-sided heart pump. And this is just kind of what that's based on. Right. So that's what we would expect to see with anemia. And normally if somebody's at rest, this isn't going to be a big deal. If they decide to run a marathon, it is going to be a big deal. They're not going to be able to do that just because they're not delivering, probably not going to deliver enough oxygen to the tissues to accomplish that. Okay, are we okay with this example? Okay. All right, and then the other one I wanted to just talk the class through here was the it's number 19 in the Guyton textbook. So it's a cardiac output calculation question. So most of you would probably done this question, I would hope that you've either done it or have it on your list of things to do. So they tell us that they set up this scenario here where they have a guy who is using 750 mL of oxygen per minute. And so that's his metabolic rate. So if he's using 750 mLs of oxygen per minute, we're probably going to have to be delivering 750 mLs of oxygen per minute to the peripheral tissues. And we do that by transporting the oxygen in the blood. And I believe that this item, basically all they gave us, they told us the metabolic rate. They gave us the hemoglobin. They said it was normal, so about 15. And then they told us the SVO2, or venous hemoglobin saturation, was 25%. Okay, and so this guy was breathing room air, and otherwise normal, except the kind of abnormal SVO2 and the oxygen metabolic rate. So if this guy is relatively healthy, he's breathing room air, nothing wrong with his lungs, then what we would expect to see in terms of the arterial blood, we would expect to see, again, a normal PaO2, 100 millimeters of mercury. If we have a PaO2 of 100 millimeters of mercury, that's probably going to be enough pressure to nearly saturate our hemoglobin. So because we have a PaO2 of 100, we could probably say that our SAT's going to be close to 100. Our carrying capacity would be 1.34 times the quantity of hemoglobin that we have, so that would give us our hemoglobin oxygen carrying capacity. So that would be about 21 mLs, or 20.1 mLs of oxygen per deciliter of blood. And the overall content here, here we're going to take a shortcut and just go with 20 mLs of oxygen per deciliter. If we wanted to be more exact about it, we could look at the oxygen carrying capacity and add to that the quantity of oxygen that's in the dissolved state. That would bring this number, well, it would change the number a little bit, but for the purposes of this example, we're just going to say that the CaO2 is about 20 mLs of oxygen per deciliter of blood. Okay, and then if we want to think about the venous blood, they give us some information, not a whole lot of information, but some. They tell us that the SVO2 is 25%. So our SAT is 25%. They don't give us a PO2. We would assume it would be lower than normal, but we don't have a number that we can be real exact about, but it would definitely be lower than normal. So with the SAT at 25, the one thing that we can say is that, well, if our SAT has dropped from 100 to 25, then what's probably happened is we've just unloaded 75% of the oxygen that we brought to the tissue. So if we unload 75% of the oxygen that's being delivered to the tissue, then what we would be left with is 25% of what was initially brought in. So our CVO2 would be equal to 5 mLs of oxygen per deciliter of blood. All right, so this is what's in the arteries, this is what's in the veins. The difference would be what we drop off. So we unloaded 15 mLs of oxygen from each deciliter of blood delivered to the peripheral tissues. So if each deciliter of blood is unloading or delivering, or unloading is probably the better term here, if each deciliter of blood is unloading 15 mLs of oxygen each time it's going around, and we need to unload a total of 750 mLs of oxygen per minute. How many deciliters of blood do we need if each of them is unloading 15 to deliver 750 mLs per minute? So if each is delivering 15, we need a total of 750 delivered. Then the quantity of blood that we would need going around in a circle each minute would be just 750 divided by 15. So that would give us 50. And if we weren't sure about our units here, so let's say we see it says 50. 50 doesn't seem right because it just seems like a weird number for cardiac output. So it may be a right answer, it may be a wrong answer. If we get to this point, we don't know what we're doing, or if we forget, well, what kind of units are we dealing with here? One of the nice things about keeping track of everything as we work the problem is if we remember what our units are. Oops. So 750 mLs of oxygen per minute. And then what were we dividing it by? We're dividing it by 15. And these are also in units of mLs of oxygen per deciliter of blood. All right, so now we're dividing one fraction by another. Looks like we're dividing mLs of oxygen by mLs of oxygen, so those cancel out. So we're still left with 750 divided by 15. And what we're left with is dividing one fraction by another fraction. And when we divide one fraction by another fraction, the numbers are fairly easy to deal with. We just divide 750 by 15. But when we divide a fraction by another fraction, what happens is that we get this number. It's still 50. But what happens is that these two variables, they flip. So if we flip those two variables, then we get some units to go along with our answer, and those units hopefully help us make sense of this. So the math is telling us that's 50 deciliters of blood per minute, and that would be a reasonable cardiac output, so that would be 5 liters per minute if we converted that over into liters. So the Guyton textbook, they give you this formula that you can take and plug everything into. While that's useful, sometimes thinking about it in this line of thought is a good way to go about doing it as well. This is real similar to the example that we had at the earlier part of the course, where we were just looking at content differences between the arteries and the veins, and thinking about, well, okay, if each deciliter is delivering 5 mLs, and where our normal metabolic rate is 250 mLs per minute, then we'd have a cardiac output of have to have 5 liters per minute in order to get those numbers to add up. All right, any questions about this one? So again, it's one that's in the book. This is just another way of wording the way that might be useful to approach something like this. All right, so I think that those are the things that I wanted to share with you or talk to you about before Friday. Hopefully this will give you a leg up on some of the concepts that we need a little bit of help on that last test. So hopefully this will be helpful for Friday. Okay, so like I said, that's all I have for you. So I can take any questions that you have at this point, if you have any. Yeah, Jordan.
Okay. I just wanted to clarify. When we're talking about chemoreceptors, we have peripheral, central. We're saying peripheral is the carotid bifurcation and central is aortic arch?
Central would be in the brainstem.
Okay, so peripheral is still aortic arch as well?
Yeah.
Okay,
Yep.
Okay, that makes more sense.
Yeah, Gina.
So the recurrent, and then it's the recurrent, and then the inferior branches off of it, correct?
Yes.
So if our voice box went out, then it'd be recurrent. We wouldn't mess with inferior, or it would be taken out, I guess, right?
Yes.
Okay.
Yes. Sometimes those are flipped too. The recurrent laryngeal nerve and the. So they kind of are the same thing. Yeah. Yeah. So the question was, are those two names basically the same thing? And the answer is yes. Yeah, Caitlin.
Can we look at question number 57 in the Guyton review?
Yep. Well, yeah, we can look at this one here. So what do they? So the basic rhythm of respiration is generated by neurons in the medulla. Is this telling us that the apnostic center is the correct answer? Or is this telling us something else? No. All right. Pneumotaxic center. Well, it's kind of in line with what we had in class. I don't know. It's not really the greatest question for us to study off of.
Okay. There was I don't know if you had looked through any of the breathing or controlled breathing in the Guyton, and I know they were never assigned, but we just went over them. Mm-hmm. But a lot of them I feel like were confusing based on what we discussed.
Yeah, and rightly so. It's completely confusing, and that's why I try to abridge everything and just give you the details that you need to know. I don't know what's so hard. Well, not about the content. I don't know why. These guys just argue with each other at these meetings. They go into these rooms and just scream at each other about what part of the brainstem controls what, and the textbooks don't line up in any of them, and that's kind of just what we're stuck with, unfortunately. Yeah.
So to kind of go off that, because I was confused, so I looked at Guyton and then I looked at Levinsky, and I guess my question is, I thought that we said that the peripheral chemoreceptors kind of responded to CO2 first, but then Guyton went into saying, well, it does, but it cares more about O2. Mm-hmm. And then that was confusing, so we're just sticking with primarily CO2 and then O2 when it drops below 60.
Right.
Okay. And then as far as the central chemoreceptors, like for example, number 56, mm-hmm. It was saying the correct answer was, I believe, hydrogen ions in the medulla. But I guess we don't have a time frame with that question, so it was confusing. I don't know if you can kind of explain it.
Yeah, it is confusing. Something that's even more confusing is that the ischemic response that we talked about the last semester when we talked about the brainstem being really sensitive to periods of hypoxia or low oxygen, and the low oxygen actually isn't the thing that drives that massive ventilatory response. It's what the oxygen gets broken, or what gets produced when there is no oxygen, which is protons and CO2. So for our class, we should just know that the brainstem is going to be sensitive to changes in pH or protons. The peripheral chemoreceptors are pretty sensitive to small changes in CO2 or protons, and the O2 sensors take forever to get turned on. Would that sum things up? I know it doesn't answer all the questions in the book, but it's...
Yes.
Yeah.
So just to clarify, we said that we're going to call them CO2 sensors in the brain and not the hydrogen?
Well, for us, we don't care for our class. That's...
Thanks.
Sure. You're welcome. Yeah, Candace.
Okay, so one of my questions is when we're dealing with alveolar ventilation increase, like normally when there is no compensation, you said if we double the 4.2 to 8.4, we decrease our CO2 to 40, to 20. If we were to compensate for that, with that kind of how you gave us with respiratory alkalosis and you told us to compensate with metabolic acidosis, are we using that same formula you gave us, like break down the bicarb into water and CO2? Because we've blown off so much.
So you're asking if we had prolonged hyperventilation, what would happen?
Yes, sir, if we're trying to compensate.
Well, the prolonged hyperventilation would produce respiratory alkalosis, and the body would adapt to that by probably bringing down bicarb levels over time. So that would be the system's compensation to respiratory alkalosis over the long haul. Would that answer your question?
When we're bringing down bicarb, like how are we doing it kind of how you told us bicarb is broken down into CO2? Like are we just producing more CO2 by breaking the bicarb down, or is it just the kidneys not producing anymore?
Right. So the kidneys wouldn't hang on to quite as much bicarb, and they wouldn't produce as much new bicarb. So we could probably take that approach. I know it's kind of a global approach, and it doesn't deal with the parts of the chemical formula, but I think that would probably be the best way to think about it for Friday. Yeah. Nick.
So under anesthesia, are we having both dead space and shunting? Are we having more dead space and less shunting? Are we having more shunting and less dead space? So.
We're going to have more shunting and more dead space, unfortunately for you.
All right, sir. All right. Thank you.
Sure. Yeah, Kaylin.
Okay, I have one more question. I'm going to try it. So whenever we have our body senses a low PO2, we said that the PO2 sensors work better with the CO2 sensors. So whenever you start picking up your respiratory rate and breathing off quicker and then develop this respiratory alkalosis and say that you drop your CO2 and then if your PO2 has not recovered, is that the uncompensated part, or is and I guess I got confused reading that, and then also I was reading in the back of Levinsky about the altitude changes, and I guess that's what happens with high altitude eventually, that you stop compensating.
Yeah, with high altitude, if we're at high altitude for long, usually our hematocrit expands, and that helps us deal with oxygen carrying problems in a low PO2 environment. As far as were we talking about a compensation to exercise that set all that off that you were describing, or?
Yeah, I think I was reading it more with the altitude, but just being like how if your PO2 didn't increase, but you dropped your CO2, and that I guess your body couldn't compensate with the increased alveolar ventilation because you're not only triggering your O2 sensor at that point. I just don't know if I read that right.
I think what I was trying to get across there with the O2 sensors and CO2 sensors, if they're both activated at the same time, usually what results is an addition of the increased ventilatory drive coming from the CO2 receptors and also coming from the oxygen sensors, and if both are getting tripped at the same time, in addition to the additive effects, usually it's increased by a multiplier in the brainstem. So if we have both of them happening at the same time, we might get both of them both additive ventilation increases put together times 2 or times 3. I think that's what I was trying to get across there. Yeah, Kaprika.
So kind of off of what Caitlin just said about dropping your your O2 while you're trying to get your CO2 in response to the sensors. So would you just add like supplemental oxygen in order to help your O2 recuperate?
I'm kind of at I don't understand what the initial increase in ventilation was, whether it's exercise or high altitude. I wasn't real sure about that one. Yeah. Jordan.
Sigh and yawn reflex, are they the same? And if not, what's the difference?
The sighs happen periodically.
Okay.
5 to probably 7 times per hour.
Okay.
Yawning happens more when we're tired.
More with what?
More when we're tired.
Oh, okay.
Right. Yeah, Candace.
When we were speaking on the neonates and we were talking about giving them too much oxygen, are we saying this is just when we're talking about premature babies or healthy babies? Like the effect of this?
Either one. The premature are more at risk because they're still developing their set points,
yes.
Whereas the older they are, the more likely they are to have some of those set points more established. So the younger, probably the more at risk they are, yeah. And it's bad for both, but it's probably worse for preterm.
Okay. And then one more question about the shunt, the pathological shunt. Would you give us how many deciliters is going over into that's not being ventilated? Versus, okay, so you would give us those numbers and we can calculate it from there?
Yeah, I'm sure I could do that, yeah.
Okay.
Melissa.
Two unrelated questions to each other, but on the transverse section where we could see, we looked at it last class and we were talking about the positioning of the lungs to help with the fluid. Why is it that you can see all the lobes if you're cut in half like that?
Oh, it was just the level at which they cut. It just happened to be the ideal level where they could just happen to see all of those lobes.
Okay.
So they just by chance they happen to pick the right level.
Okay.
I know, and in some of if you're looking at it from a superficial view, it's not as apparent. But if we look at the fissures are, from some of the angles, it looks like they're straight lines, but they're actually they're angled quite a bit. Okay. So if we do a cross section, we're more likely to run into one of those that we're able to see. Yeah.
Okay. Thank you. And then the other question is, are we saying that the chemoreceptors that are in the brainstem, that they don't adapt?
They do not adapt very much, no.
Okay.
What can adapt or what can keep things constant is the CSF buffer system. So if we have somebody who's acidotic forever, their CSF pH should be 7.31. So when we have that type of system preventing long-term changes in the brain CSF, that kind of precludes the brainstem adapting to those long-term conditions. Yeah, you're welcome. Yeah, Samantha.
So talking about our premature babies and the, I guess, hypoxic response when we take them off their high FiO2s in the alveoli. So their body sees that as almost like an alveolar shunt and causes the HPV response.
Yeah, that would be part of it. And so if it thought it was at an oxygen deficit, then the whole body would respond the way a normal body would respond to an oxygen deficit. So whether it would be hypoxic pulmonary vasoconstriction or growing new blood vessels to help out with oxygen delivery, because we think that we're at an oxygen deficit, both of those would be problematic. Yeah.
So when we have that HPV response, although technically those alveoli are ventilated, how are we getting oxygen exchange? Because wouldn't they all kind of look that way?
Mm-hmm. Yeah, they absolutely would. So it would make it a real hard time for the right heart to pump. And luckily and unluckily, the blood vessels in our lungs, they're not as strong as the blood vessels out in our periphery. So they'll be able to redirect blood flow, but completely clamping off blood flow is another story.
So would this HPV response be pathological?
Yeah. Distant sights, anything from you guys? All right, cool, go ahead.
In the Levitsky book, chapter 3, I think it's question 5. So on the last exam, you did a similar version of this question, and I was just trying to remember how it was set up. I think you asked what RV was.
Uh-huh.
And so it would just be doing the same thing that we do here in the Levitsky book, but just solving from that patient starting at RV instead of FRC.
Oh, 3.5?
Yeah.
Yeah, I just asked you for FRC. I didn't change it at all. I just changed the volume.
Okay.
Yeah.
Thank you.
You're welcome. All right, Jordan.
Okay. I'm getting kind of confused. When we're talking about COPD and we were discussing CO2 building up in the blood, and you said that if we had a high enough concentration of CO2 going into the functional alveoli, we would have a steady state. So you're saying that we would have this increase of CO2 in the body, arterial blood, and then, but we're still putting, I'm not understanding what this steady state means.
The steady state would mean that we're disposing of CO2 at the same rate that we're producing it.
Okay.
So if we have impaired ventilation, one way to increase the CO2 that's delivered to the good alveoli would just be to let the blood PCO2 increase.
Okay.
And once it gets to a certain point, it's eventually going to get to the point where our lungs are breathing off the same quantity of CO2 that we're producing. So that would be steady state. So just like creatinine with the kidneys. So if somebody has kidney failure, their creatinine is high. But the high creatinine is what allows the fewer remaining nephrons to get rid of the same quantity that's being produced each day.
Okay. And then just one more in regards to this.
Mm-hmm.
You said the escape mechanism to fix, if we had the CO2 sensors that were out of the picture and we were just manipulating the O2 sensors, you said the escape mechanism would be to be CO2 buildup in the brain? I'm not understanding that either.
Yeah, so if we go ahead and screw up, so if we have somebody who has end-stage COPD, they have high blood PCO2 as it is, and if we were to go ahead and switch them from breathing room air, if they were making it on room air, if we were to go ahead and put them on oxygen, they would have no reason for their body to breathe. And they would probably be apneic until the point in time where their CO2 is built up so much because they're apneic that it's getting to the point where it raises brain PCO2 levels to the point where the brainstem is going to tell the diaphragm to contract because it's becoming sufficiently bad enough to the point where it's getting to the brain and messing with the controllers there. Does that help? Okay. You're welcome. Yeah.
So with that steady state, we're having an increased arterial CO2. Would we have an increased alveolar CO2 as well? And then would we see that as an increased CO2 on our end tidal, or would, I guess where am I going with this? I'll just leave it at that.
Yeah, in some cases we might, in some cases we might not. It would depend on what's causing the elevated alveolar or the elevated blood PCO2, and whether or not we are looking specifically in just healthy alveoli or the collection of all the alveoli emptying at once. So if we have if the CO2 problem is caused because we have tons of alveolar dead space, then our alveolar or end-tidal PCO2 is probably going to be a little bit lower than what our arterial blood gases are showing. And usually, just as a rule of thumb, if we can compare end-tidal versus blood gas numbers, the further we are away from each other, the worse off the situation is. Yeah. Yeah, Caprica.
So back to what George was saying about letting the brain CO2 levels build up. Is that because we have readjusted in our normal chemoreceptors that we have to allow the brain to start kicking in when we put a COPDer on oxygen?
Yeah,
Okay.
yeah, right. Their peripheral chemoreceptors might be so far out of the picture that they're not going to be good for much in terms of responding to CO2 because they're used to seeing it so high they no longer care. Okay. Yeah, Candace.
This is my last question.
All right.
On the last test, when you had given us the problem of, I think we were to figure out how much was the quantity of O2 in 2 deciliters of blood when we drew up, I guess, in a test tube. Was that an ABG or venous?
It was from a pulmonary vein.
A pulmonary vein. Oh, thank God, dog. Okay, thank you.
You're welcome. All right, distance sites, you got anything? Little Rock, the people who are there? No? Shreveport, Colton, anybody? Okay, Mary.
Maybe. So on the pulmonary shunting question that we went over last lecture, we had said that if we have an inspired of 150 and that would give us an alveolar partial pressure of 100, that we would have 0.3 of dissolved O2 in the blood. And then when we add 600, or if we have now an inspired of 600 and we're adding a pressure of 450 on top of that, I was just confused as to how we got the 0.9, because in my head, if we have 450 in addition to the 0.3, then I would feel like the 450 total would be 0.9 adding to the 0.3 to give us then 1.2 mLs. So I just wanted to clarify that going into the final in case my thinking, if I was just not connecting something.
Maybe some of the confusion might be that we don't normally deal with these numbers here with the inspired gases. We're usually looking at alveolar and then blood gases. So if we had, and this is definitely an oversimplification of what's going on here, but it still works out. So the PiO2, if it's 150, if that gets us 0.3, then we might say that if we have 4 times that amount of pressure of inspired oxygen, that we would get about 4 times as much oxygen in the dissolved state. So that would give us 1.2, and that would be 4 times 0.3. And the portion that's coming from the PiO2 that's above 150 would be, we're just kind of approximating that to be 0.9. So if we were to add both those up, we'd get about 4 times what we normally have. Does that help? Okay, you're welcome. Yeah.
Okay, this is an anatomy question. For the false cords, do they sit on top of the conus elastis?
Technically, yes. Yes. I won't ask you that on the test. Okay. I won't ask you anything about the false cords on the test. They will absolutely not be on the test. Yeah, Jordan.
I think this might be my last one. For the graph that had, I don't really know how to tell you to get to it, where it's at, but it's the peripheral chemoreceptor effects 1. and it has the different lines. We have different PaO2s, like of 100, 50, and 35. So for the PaO2 of 35, I'm not really understanding how it's correlating to the PaCO2. Are we saying
this one here? Oh, sorry.
I was like, nope.
That one?
Yes. Are we saying if we had a PaCO2 of 40 and a PaO2 of 35, that if we draw that line all the way up, it would just be a crazy amount of alveolar ventilation?
Which one are we?
The PaO2 of 35.
This one here?
Yes.
So if we have a PaO2 of 35 and a PaCO2 of
40?
30.
Or are we saying 35?
35.
Okay.
The low CO2 would kind of be depressing the respiratory drive, but at this point here, but it would still be way above normal alveolar minute ventilation, which would be 4. So here we're looking at least twice that.
Okay.
So if we have a low arterial PO2 and if we have just small increases in arterial CO2, that results in huge increases in minute ventilation.
Okay, that's what we're saying.
All right. Anybody else? All right, just insights, you're all good, hopefully? All right. Excellent. So I want you guys to do good on Friday. You know what to do between now and then. Study up. We'll see you. What's our test time at noon? Noon to 4? Good. All right, we'll see you at noon on Friday.